This is part 2 of lecture 4.2, Equivalence Relations. In this video, we will define a partition of a set and describe the connection between equivalence relations and partitions. We begin with the following result. Let R be an equivalence relation on a non-empty set A. For any elements x and y in A, x is related to y if and only if the equivalence class of x is equal to the equivalence class of y. And x is not related to y if and only if the equivalence class of x and the equivalence class of y are disjoint, that is, have empty intersection. To prove part 1, assume first that x is related to y. Let x prime be an element of the equivalence class of x. Then x prime is related to x. Since R is an equivalence relation, it is transitive. So x prime is related to y. Thus, x prime is an element of the equivalence class of y. Hence, the equivalence class of x is a subset of the equivalence class of y. By repeating the above argument with x and y interchanged, we can show that the equivalence class of y is a subset of the equivalence class of x. Therefore, the equivalence class of x is equal to the equivalence class of y. For the converse, assume that the equivalence class of x is equal to the equivalence class of y. Since R is an equivalence relation, it is reflexive on A. Thus, x is an element of its own equivalence class. So, x is also an element of the equivalence class of y. Hence, x is related to y. Thus, x is related to y if and only if the equivalence class of x is equal to the equivalence class of y, and part 1 holds. To prove part 2, we first show that for any elements x and y in A, the equivalence class of x and the equivalence class of y are not disjoint if and only if x is related to y. Indeed, if x is related to y, then x is an element of the equivalence class of y. We know that x is an element of its own equivalence class since R is reflexive on A. So x is an element of the intersection of the equivalence class of x and the equivalence class of y. And thus, the equivalence class of x and the equivalence class of y are not disjoint. Conversely, assume that the equivalence class of x and the equivalence class of y are not disjoint. Then some object z is an element of the intersection of the equivalence class of x and the equivalence class of y. So z is related to both x and y. Since R is an equivalence relation, it must be symmetric. Thus, x is related to z. Hence, x is related to z and z is related to y. Since R is transitive, it follows that x is related to y. This proves that the equivalence class of x and the equivalence class of y are not disjoint if and only if x is related to y. It follows that the equivalence class of x and the equivalence class of y are disjoint if and only if x is not related to y. Thus, part 2 holds. Observe that for any equivalence relation R on a non-empty set A modulo R is a subset of the power set of A. That is, A modulo R consists of subsets of A. Furthermore, the following are satisfied. For any P in A modulo R, P is non-empty. This follows from the fact that R is reflexive on A, so each element small a is equivalent to itself. Hence, each element small a is an element of its own equivalence class. The union of all sets P in A modulo R is equal to A. Indeed, it follows from the proof of number 1 that for each object small a, there is a set P in A modulo R which contains small a. Thus, A is a subset of the union of all sets P in A modulo R. Since this union is also a subset of A, equality follows. For any sets P and Q in A modulo R, either P is equal to Q or P and Q are disjoint. This follows immediately from the theorem in the previous slides. This leads us to the following definition, which generalizes the above properties of A modulo R. A partition of a non-empty set A is a family F of subsets of A satisfying the following. First, every set in F is non-empty. Second, the union of all sets in F is equal to A. And third, any two sets in F are either equal or disjoint. Suppose that A is a non-empty set. The set of all one-element subsets of A is a partition of A. The set consisting of the set A is also a partition of A. The singleton with element 0, the set with elements 1 and 3, and the set with elements 2, 4, and 5 form a partition of the set with elements 0, 1, 2, 3, 4, and 5. The set of rational numbers and the set of irrational numbers form a partition of the set of real numbers. The next two theorems describe the connection between equivalence relations and partitions. First, let R be an equivalence relation on a non-empty set A. Then A modulo R is a partition of A. This follows immediately from the previous theorem and remark. Next, let P be a partition of a non-empty set A. Then there is an equivalence relation R on A with A modulo R equal to the partition P. To prove this, define R as follows. For any elements A and B in the set capital A is related to B if and only if some set P in the partition contains both A and B. We will show that R is an equivalence relation on A. Let A, B, and C be elements of capital A. First, we show that R is reflexive on A. By the definition of partition, capital A is equal to the union of all sets P in the partition. So small a is an element of the union of all sets P in the partition, and thus, by the definition of extended set union, some subset P in the partition contains A. The statement A is an element of P and A is an element of P is clearly true. So A is related to itself. Hence, R is reflexive on the set capital A. Next, we show that R is symmetric. Assume that A is related to B. Then, some set P in the partition contains both A and B. Equivalently, some set P in the partition contains both B and A. So B is related to A. Thus, R is symmetric. Finally, we show that R is transitive. Assume that A is related to B and B is related to C. Then some set P in the partition contains both A and B, and some set Q in the partition contains both B and C. So B is an element of the intersection of P and Q, and thus P and Q are not disjoint. It follows from the definition of partition that P must be equal to Q. Thus, A and C are both elements of the set P. Hence, A is related to C. Therefore, R is transitive. This proves that R is an equivalence relation on A. We now show that A modulo R is equal to the partition P. A subset X of A is an element of A modulo R if and only if X is equal to the equivalence class of some element small a in capital A. Equivalently, X is equal to the set of all objects B such that B is related to small a for some element small a of capital A. By the definition of the relation R, this is equivalent to X equal to the set of all objects B such that B and A are contained in some subset P in the partition for some element A in capital A. Note that if subsets P and Q in the partition both contain the element A, then P equals Q. So it follows from the definition of partition that any element A in the set capital A is contained in a unique subset P in the partition. Thus, the above statement is equivalent to the condition that X is equal to the set of all elements B contained in some subset P in the partition. In other words, X is equal to some subset P in the partition, which is equivalent to X being an element of the partition. This proves that A modulo R is equal to the partition P, which completes the proof of the theorem. To summarize, let A be a non-empty set. The last two theorems show that any equivalence relation R on A determines a partition P of A, and any partition P of A determines an equivalence relation on A. In both of the above, A modulo R is equal to the partition P. And for any elements A and B in capital A is related to B if and only if A and B are both contained in the same subset in the partition. You have come to the end of part 2 of lecture 4.2. Before you proceed to lecture 4.3, you are strongly encouraged to do the exercises given at the end of these slides. Thank you for your attention.